intermolecular forces that we're going to talk about today. These are the four basic ones right here. Oh my goodness, come on, computer. These are the four basic ones right here. Dispersion, dipole dipole, hydrogen, and ion dipole. Okay? I would write these down. Yep, the four. Oh my gosh, Christian. I know, I'm going to make you write these down. Oh, is that a Christian, why are you being mean to me? This is Christian. No, okay, so dispersion. So let's talk about each of these in some greater detail. All right? Each of these in greater detail. And it has, I like that it has here the present, like what happens with that, and what it looks like, and the strength of the force. So what is the dispersion force? Sometimes people call it the London dispersion. So because it was discovered in London, I think. What does dispersion mean? Anybody? To disperse. What is dispersing?
It means to spread out.
It means to spread out, yes. So to spreading out, so for instance, you've learned about the dispersion of things like in solutions, right? That things always want to be in equilibrium, right? Like osmosis. Are we familiar with osmosis? Yeah. Okay. So this happens because of Coulombic interaction. So the electrons push on each other, right? In between the molecules, right? Yeah. They don't. So the electrons in one molecule, let's say that this is a carbon dioxide molecule. Now let's just do it molecular oxygen, okay? Molecular oxygen, and you have the electrons in the molecular oxygen going around the outside. And then you have another molecular oxygen. So this is O2, and this is O2. This isn't O and O, this is O2 and O2. So again, we're not talking about bonding between atoms. We're talking about the forces in between molecules. Okay, the forces in between molecules. So this is a molecular oxygen, They push away from each other. And what happens there is that we get a slight moment of polarity. A slight moment of polarity, meaning that on one side, this electron is pushing away this electron. So they push away from each other. It's just like two magnets. Okay, just like two magnets of equal or of similar polarity. They push away from each other. So they want to disperse into the air. Or, yeah, in this case, it is in the air, right? They want to get away from each other.
Now the symbols mean charge, right?
Yeah, so yep. Okay. Questions on how that works? So any molecule, the electrons in that molecule will push against the electrons in other molecules, keeping each other away from one another.
So positive charge can only have forces with negative
Right, well, they align themselves in a certain way where they disperse because of those charges. And it's not like this is really positive, it just is kind of a lack of a negative because the electrons get pushed over to that side.
So London dispersion is just like they align themselves and then they're kind of weakly bonded because.
No, they're not weakly bonded, they're kind of keeping each other at a distance because the electrons don't want to get too close to each other.
Well, yeah, but wouldn't that make them kind of a weak bond? Because
There is a tiny amount of attraction between the negative part of this and the positive part of this, but it's extremely weak. Extremely weak. They want to keep their distance, but so the way that it was explained to me is that people in London don't want to get too close to each other, even though they're all Londoners. They're all kind of like, hey, like from a distance, and the reason why I think, let me think here. I'm trying to go back into my chemistry brain. Imagine a whole bunch of people in London walking around with umbrellas. Okay. Their umbrellas don't want to touch. They don't want to touch umbrellas, and so they kind of keep each other at a distance. The London dispersion forces. Does that make sense, Christian?
So dispersion only applied to atoms, or does it also apply to compounds?
So it's not atoms. These are molecules. It can be an atom. So like, for instance, if you were to look at neon, let's say this is neon and this is neon, right? They're not going to bond together, but they are going to have this weak interaction between the molecules because of the interaction between their electrons.
So like this isn't going to become an O4 molecule. It's
Right.
gonna be two molecules of force.
Right, there's slight forces in between the two molecules. This isn't bonding together. It is just a slight interaction. Okay? Dipole dipole. Let's see here, what is this? This is carbon. What is the red? Is that nitrogen?
I thought it was oxygen.
Red is oxygen. Carbon, oxygen,
And then,
COH2,
yeah.
right? So these are polar molecules. Dipole dipole only happens in polar molecules because the positive end of one molecule is attracted to the negative end of the other molecule.
So what's a dipole?
So a dipole is something that has two poles,
Oh,
right? The positive pole and the negative pole. So dipole dipole that means the attraction between two polar molecules.
but the one above is also dipole dipole.
No, they're not polar. They're not polar molecules.
Any of the difference in
The difference in the polarity is because they're close to each other. Exactly. So this molecule by itself has no charge, right? Has no charge anywhere in it.
COH2 has a charge by itself.
Yes, it has some. So this is the oxygen, right? The oxygen has a lone pair of electrons over here.
Okay.
Does that make sense?
Yeah.
So its lone pair of electrons over here is repelling this area, which these hydrogens have lost their electrons to the carbon, thus making them positively charged. So you have two polar molecules. They're the same kind of molecule, and they are going to want to align themselves in that orientation. Okay?
Sure.
Sure. All right. Now, let's look at hydrogen bonding. Molecules containing H bonded to F, O, or N exhibit hydrogen bonding. Why would this be the case? Who can tell me? I wish that a teacher would have explained this to me earlier. Oliver?
So how come it has to be those ones? Because, I mean, it makes sense that H and then those three, like, that would make a polar molecule. But this isn't dipole dipole. What makes this different?
So this is specific to hydrogen because hydrogen only has one electron. Okay? Dipole dipole, so hydrogen bonding so the way that I kind of think of it is hydrogen bonding is kind of a subset of a dipole dipole. It's kind of like pasta and spaghetti, right?
Is it stronger?
It is stronger.
Yeah.
It's stronger.
Strength goes down as it goes down.
Strength goes up.
And strength goes
Yeah.
down. Oh. Wait, why does the strength go up?
What?
Why does the strength go up?
How does the strength go up? So this interaction is extremely weak because there's really no charge involved. It is simply just like the electrons pushing on each other, right? Here we have two polar molecules that are acting like magnets.
But the charge isn't that strong because, well, the molecules have a charge. In hydrogen bonding, since hydrogen only has one electron, it loses it, then it has no electrons.
Right.
Whereas up there, they could have more electrons. They would just be a smaller.
So here are the hydrogens, right, in H2O. These are water molecules, right? Here are the hydrogens. Those hydrogens have been stripped of their only electron, and they do not have any inner shells of electrons. So it's essentially a naked nucleus hanging out here that is positively charged. In the case of this here, this dipole, this oxygen has lost, or sorry, this not this oxygen. This what am I thinking here? This oxygen is attracted to these hydrogens, okay? But this carbon is creating a dipole here, right? Here. But the pole in between these two is not as strong as it is between these two. Now that I think about that, the way that I'm thinking is not making a lot of sense. But the hydrogen bond is stronger than a normal dipole dipole or just a general dipole dipole because of there is no shielded electron. There's no electron shells underneath. Yeah.
So what is HF?
HF?
Yeah.
Hydrogen fluoride?
Can we get some?
I don't think that would be a good idea.
Why?
I think it would be really corrosive.
It wouldn't be like a really strong crystal or something?
Hydrogen.
Or you could just get some water.
Hydrogen fluoride is a chemical compound, HF, it's a colorless gas. It's an industrial source of fluorine. Don't look here. I mean, the CDC has a thing on it. So we use hydrogen fluoride to make history, aqueous solutions.
We would refer to international as outside of other countries, outside of our country. Like, you know.
Yeah, okay, so upon contact with moisture, including tissue, so including skin, hydrogen fluoride immediately converts into hydrofluoric acid, which highly corrosive and toxic, yeah. Not a good idea.
Why does it?
Because it interacts with the oxygens.
Okay, so there's oxygen, iron, and like
Yes. Oxygen loves to react with stuff, thus burning.
well, what about like nitrogen?
Nitrogen isn't that.
Well, what makes oxygen more reactive than nitrogen and fluorine?
Well, it's not more. The hydrogen fluoride reacts with the oxygen, and it pulls the oxygens and hydrogens, because converts into hydrofluoric acid. Hydrofluoric acid. So, water. Hydrofluoric acid is a solution of hydrogen fluoride in water. So that's the whole thing. Like when hydrogen fluoride interacts with water, it becomes hydrofluoric acid.
So is hydrofluoric acid
It's a
or is it just like
it's a solution.
fluoride dissolved in
It's not a molecule, it's a solution.
So
It's hydrogen fluoride in water.
Okay. And what makes that acid?
It wants to pull away. So acids have excess hydrogen ions. Yeah. So we'll talk about like pH and stuff. It's all about the excess hydrogen ions. So the hydrofluoric acid ionizes the hydrogen and the oxygen in the water. So it's no bueno. Okay. All right, so last one, ion dipole. Ion dipole, which makes a lot of sense. So here we have a bunch of water molecules. So a water molecule is a polar molecule, right? So hydrogen bonding is a type of dipole-dipole. This is always how I explain things that are subsets of other things. It's pasta and spaghetti. Not all pasta is spaghetti, but all spaghetti is pasta, right? Not all dipole-dipole are hydrogen bonds, but all hydrogen bonds are dipole-dipole. Okay? So we have a dipole here, a water molecule, being attracted to an ion. In this case, it is a positive cation, or we want to say it like English, cation.
Well, actually, not all spaghetti is pasta.
Ben, did you really just look up and see what is spaghetti is not pasta? Okay, Ben, I get it. You can make spaghetti in different ways than making it out of pasta, but that's the way that I think about it, okay? How about this? How about this? Every apple is a fruit, but not all fruits are apples. Every square is a rectangle, but not every rectangle is a square. Okay, I'll start using the apple fruit situation, okay?
Every function is a relation, but not all relations are functions.
Yay, math. Not all relations are functions. Okay. Dipole ion or ion dipole interactions are made between an ion of a molecule that is an ion, right? So it is a positively charged molecule Not a molecule that has a positive charge on one side. It is a positively charged molecule. And a dipole molecule, a molecule that has a positive and negative side.
What if you have a positively charged molecule and a negatively charged molecule?
Then that becomes an ionic. It's a positively charged molecule and a negatively charged molecule, then you will get a series of chemical reactions because they want to be neutrally charged.
Well, what if they're both non-reactive?
I cannot think of a single ionic molecule that is not reactive.
Look what is.
How come
Because it wants to be at a lower energy state.
How come when you have a positively charged molecule, you have a whole bunch of
Dipoles.
dipoles sticking their negative end in their space?
The negative end in its face. So this does not generate this does not generate a reaction because the water molecule in by itself is at a lower energy state than it would be if it got ripped apart to be part of the.
Well, what about the other one? That wouldn't be. Isn't there?
That's true, but it doesn't have it. But it has not created enough charge, or it doesn't create enough energy differential to disrupt the stable configuration of that molecule. Yeah.
What's the name of the charge symbol?
It is gamma. Yep, it's lowercase gamma.
So like the gamma function.
Kinda, yeah.
The gamma function.
Okay, so questions about these 4 different types of intermolecular forces?
What are we going to do?
What are we going to do? What?
What are you going to apply this to?
How are we going to apply this?
Yeah.
That's a great question. We're gonna watch the daily video from today, and you will see. All right, I'm going to end the video here. So go watch the daily videos for topic 3.1. People at home, 3.1.